Okay, hello. Um, so today we have class 10 on MongoDB. So we're going to move on to a new topic within the NoSQL space. So the last time we spoke about key value stores, and we saw in the lab about Cassandra. We also spoke about column families. So today we're going to move on to the third category of system, which is document databases. So in terms of document stores, we spoke a bit about, which we can't see because this thing, I wish there was a way to put it horizontal, but okay. So we saw key value stores, which are just a distributed map where we have keys and values. We saw also, it's okay. We saw also multi-dimensional maps. So this is the tabular stores. And today we're going to talk about document stores where the value is the document. Okay, I wonder is there, yeah, I'll put that there. Okay. So today we're going to focus on one particular document store, which is called MongoDB. Maybe you've heard of it, or maybe you've worked with it. So it stores JSON documents. So hopefully you're familiar with JSON. So in terms of our ranking of database engines, the most popular NoSQL store we have here is MongoDB, which is in the 5th position. And it's a document store as we see here. So it's a very popular database system. It's the top NoSQL system in this list, the 5th overall. So in terms of MongoDB, what we're basically going to be able to do is to index JSON data. So we can index JSON data like this, where we have strings and numbers and arrays of values and so forth. So we can also have nested objects or documents. Here, the schedule itself, the value is the document. So you've seen JSON before, I guess. In the context of MongoDB, we also have a different format called binary JSON or BSON. So binary JSON basically adds some additional types, such as we can define a type for our IDs of documents, and we can define some types like, for example, dates in a standard format. So the data types of JSON are these, where we have strings and doubles and arrays and booleans and objects and lots of cool data types. In the case of BSON, we add some more. So we add some object IDs, we add some dates, and we also have some for geographic points and some other stuff that we'll see. We'll see a little bit later. Okay, so in the context of MongoDB, the core data model effectively involves mapping keys to values. And these values are BSON documents, or I'll just say JSON to keep things straightforward, an extension of JSON called BSON. So we see we have the key here, and in the document, we see that this key corresponds to the object ID of the document, and we have a bunch of data associated with the JSON document. So a MongoDB collection then collects together all of the similar documents. For example, here we have documents relating to TV series, where we have information about, here in this case, JSON documents describing TV series. So we can have different collections, and we can add all of those collections into a database. So a database, essentially, this one, in this case, is called TV, collects together collections that in themselves contain similar types of JSON documents. So for some commands that you'll need in the lab on Wednesday, when we're going to be playing with MongoDB, we see the command to use a database, which we just say use and the name of the database, tvdb, for example. So this will load the database and create one if it does not exist. If we want to, once we've logged into MongoDB, see all the available databases, we can write show dbs. If we want to see what's the current database we're using, we can just type the command db. And if we want to drop the current database, hopefully with caution, so you think twice before calling this command, we can do db.drop database, and we'll just delete the database that we're looking at. Okay, so if we want to create a collection series within the current database, we can use db.createCollection and the name of the collection we want to create. Apologies. If we want to see all of the collections, show collections. If we want to drop a collection, db.the name of the collection we want to drop, .drop. And to clear all the documents from the collection, db.series remove, and this is a query that will match all of the documents. So we'll just remove all of the documents from the collection. It's a very common use case in MongoDB that we want to use it for caching some data. So we have some application and we want to maybe cache some data that we've recently computed. We can create for this a capped collection, which will keep only the most recent documents, and we can set two types of cap or limit. We can set a limit in terms of the size and bytes of the collection, or we can set a limit in terms of the number of documents in the collection. If we reach one of these limits, what we will do is insert the new document and then delete the oldest one that was added. Okay, any questions, or it's okay? All good? Okay, so inserting data. So a lot of this is maybe syntax, and I'll if you have questions, let me know. I'll go through it quickly, but do stop me if you have a question. Also in Zoom. So in terms of inserting documents, so what we have here is a document, a JSON document that we're inserting. Notably here, we don't specify an ID. So we write db.the name of the collection we want to insert, .insert, and then give the document, and everything is great. If we like, we can also specify the ID explicitly. So if we don't specify the ID, in this case, it will create one for us in MongoDB. If we want to specify the ID, we can do this. However, this ID can't already exist. Otherwise, this command will fail. So we assume this is a fresh ID. If we wanted to override an existing ID, we can use either save or update to do that. So for example, here's the command with save, where the idea is to overwrite the document that already exists with this ID with some new document. So this save will overwrite the existing document. Okay. So MongoDB in general doesn't really have a clear formalism associated with it. It doesn't have, like in the case of relational databases, we have the relational algebra, and that makes things nice and easy to understand. We learn 6 operators, and then we can put them all together into complex queries, but we know what's going on because we've clearly defined the operators. So MongoDB kind of lacks this kind of formal definition, which is maybe nice because web developers maybe, or certain users don't really care about formal things, but it also makes it a little bit difficult sometimes to know what kinds of results MongoDB will return. So in this case, although it doesn't really exist in the MongoDB documentation, I'm going to talk about these features as if they were selection, if you remember selection from the relational algebra. So what does selection do? It basically says what rows we want to return in the relational algebra. In this case, it will tell us what documents we're going to return. So we're going to start with a query without any selection criteria to start with. So we'll say db current database.series, the name of the collection, .find. And what this will get is it will return all of the documents in the collection. Yeah. So this might be a lot. In this case, we've only inserted one document. So we get back the document in this format here in JSON format. So if we wanted just to sample one document to have a look at what the documents look like in a collection, we can rather use find one. The last results looked pretty ugly. So if we wanted to, we can call on any command in MongoDB that returns JSON. We can add this .pretty command, and what this will do for us is it will print us the JSON documents in a nice indented, easy to read format. So it's a pretty useful, no pun intended, a pretty useful function. Okay, so selection. So what if we don't want to return all of the documents, but rather we'd like to say, oh, just return me the documents with a certain genre or a certain runtime? We can do this using Sigma for selection criteria in MongoDB. So the first selection criteria we have is equality, where we can say, okay, give me all of the documents that have some key or some attribute equal to some value. So in this case, give me all of the documents that have type scripted. We see that this document here has type scripted, so we return the document. Yeah. So results here would actually include the ID, but for brevity, sometimes I'm going to leave it out just to make the examples a little bit more readable. So just to keep in mind in practice, yeah, this result would have an ID here. This part. Okay, so we also can access nested values. So in JSON, we can have nested documents as values. And in this case, we can use this syntax rating.average equal to 9.4 in order to access this nested value here. Yeah. So essentially we say rating.average 9.4 and we run this query and we get the document as we expect. So we can use this dot as an abbreviation to access nested values. We can do equality on nulls. So we have nulls in JSON data. We have nulls as well in MongoDB. So what will this do? In this case, rating.average will match two cases. It will match the case where the value is really null in the data. And it will also, as we see in this case here, so we get the result because the average is null. And it will match a second case, which is when we don't have any, key, or we have no field with that key. So essentially here we have no information about rating average. So we'll also return this document here. So it's like it not exists as well. Yeah. So when the field doesn't exist with the key, we also return the null case. A value can also be an object or a document. So here in this case, we're matching on equality that the rating is exactly this object here. So if I say object or document, they're interchangeable terms. So our rating has this object here, average 9.4. We see that this exactly matches here. So we get a hit and we return this document. So you might be asking, okay, well, that's an exact match. What happens if in other cases? So what happens, for example, if we have a partial match where we have an object which is clearly contained in the object in the document? So we see both here in the query 9001, and we see that there's a match here, but it's a partial match on the document. We're not matching the entire object or document, just a small part of it. So in this case, we get no results. We need to have a full match on the object. Yeah. So this leaves us with a last doubt, hopefully. Any ideas what the last doubt might be? What happens if we have everything, but they're in the wrong order? They're in a different order to the document. Does the order matter? Yeah. And the answer to that question is yes, the order matters. Here we get no results because the attributes, the keys or the fields are in a different order. So we have votes average here, and in the data we have average votes. So MongoDB cares about the order of the elements. Yep. Okay, so we can also do selections on arrays. So how do selections on arrays work? We can specify something like this, where we have genre and we have science fiction and thriller, and here in the document we have genre and science fiction and thriller. So we get a nice match. We have exactly the same array in here. Okay, so same questions as before. What happens if we have a partial match? We just have one part of the sum of the elements, maybe, or subset of the elements in our query array versus the document. In this case, no results. We need to match the full array, which leaves us with one last doubt. What might it be? Yeah, does the order matter? The order does matter. So if we swap the order of these two elements, then we see that we get no results. So the order of elements matters in both. So it's similar for objects and arrays, that we really need to have an exact match with the same order and the same elements. Okay, so we have this feature of MongoDB, which looks nice in theory, but will create some weird complications later. Okay, what's the nice feature? The nice feature is that if we're looking for genre with thriller, for example, and if there is a thriller inside an array for genre, then we'll match. So we'll transparently look inside the arrays to see if there's something that matches our equality query. Yeah. So not only will this match if we have directly the value thriller here as genre, but it will also match if we have an array in which thriller is found. So we get this result here. And this looks nice. It will create some complications. We'll see in a while. But okay, so we're kind of mixing two things here. So just to show how it mixes two things, if we have these two documents here, where we have a name A, value 5.6, and name B, value 5. If we search for 5, we'll both match the equality here and the contains in the array here. Yeah, so we'll actually return both documents. So somehow we're slightly conflating two different types of operations that I'm sure won't cause any complications later. Okay. Cough. Okay, so inequalities. We can also, rather than searching for exact matches on values, We can search less than, greater than, less than or equal, greater than or equal, and not equals. Yeah. Quick example of that. So less than 70. So this time we're searching for runtime not exactly equal to some value, but rather runtime's less than 70. We have runtime 60 here. So we get a match. Yeah, we return this document here. So we have some options as well for matching one of multiple values. So like in SQL, we have this in keyword. We can do something similar in MongoDB. And we also have not in SQL. In this case, we have NIN, not in MongoDB. Yeah. So this matches any value here, and this matches basically the value is not in this array, and it will also match if the key does not exist. If this thing here, there's no value or no field with that key in the document. So in here we have our in case where we have runtime in 30 or 60. This is basically saying runtime is 30 or runtime is 60. We see that here we have a match. So we return this document and all is good. So in this case, we have genre in noir and thriller. And in our document, we have genre, science fiction, and thriller. So what do we think? Do we think it will return this document? Yep. Yep. So it will. It will return if any element of this array is in this array. So if the intersection of the in and the array in the data is not empty, then it will return the result. So if any value of the array is in the in, then we're good. So we can also combine selection criteria. So here we see sigma and sigma prime, which are basically any selection criteria we've seen. We can combine these with Boolean connectives like and, or, not, and nor. Nor being the negation of or. So it would be or is true if something is true, and then the not of that would be if they're both wrong, if they're both false. Okay. So nor would be this is false and this is false, I guess. So okay. Naturally, we can also nest such conditions. So really, in this case, nor is completely redundant because we could just do a not or, but okay. So let's have a look at and. Here we have a selection criteria with and we have an array in which we list the ands. We have runtime in 3060. The runtime is either 30 or 60. This is not an interval, a list of exact values. And the name is not equal to lost. So we're looking for a series that have a runtime of 30 or 60 minutes that are not lost. And we see that this document matches all of the criteria. So we return this document here. No surprises there. Okay, so next we have attribute exists or not exists. So we're looking to see if we have a field that has the attribute with the value key. Yeah. So as an example, here we say name exists true. So find all of the documents that have a name. And we see that this has a name. So we return this document here. And this will check that the field exists and it will return true even if the value is null. Yeah, so as long as there's some reference to fields with this attribute here, then we're good. The opposite of this is attribute not exists, where we put exists false. So in this case, we're looking for documents where there is no name, and we'll get empty results here because this document has a name. Okay, so something different from SQL and some other query languages is that we can do selections on arrays. Yeah, so we have specific functions that will not just look inside arrays, but will actually try to match arrays specifically. So the first selection criteria relating to arrays that we have is called all. And as you might guess, what it's looking to see is if the array contains all of the elements that we specify here. So we're looking here, we're going to match with documents that have a field with the attribute genre and have an array where all of these elements are contained. So it contains comedy and it contains sci-fi. Yeah. So in this case, do we return the document? We're going to return the document, yeah, because it contains all of the elements that we had in the query. So all the values are in the array. So the next criteria is the match one selection criterion, where we specify element match, and then we specify a list of selection criteria. So what we're looking for is that some array element matches all of the criteria. Yeah. So we need some elements to match all of the criteria. So does element 1 here match all of the criteria? No, it doesn't match the greater than 1. What about 2? Is 2 greater than 1 and less than 3? That looks pretty good. Okay, so it matches all of them. And 3 doesn't match less than 3. But we do have one array element, 2, that matches the selection criteria, so we return this document. Yeah, so if any array element matches the list of all of the selection criteria here, then it's a match and we return the document. Okay, so one element matches all criteria with AND. We can also match arrays with exact size. So we can say, give me all documents where the series is an array of length 3. So we use size for this and we do 3. And we get the document back as we might expect. Just to mention, it's only possible for the exact size of an array. We can't do, for example, give me arrays of length greater than 2 or length greater than 3. And there's no obvious way I could find to emulate this with other features. So we can only search by exact size of an array. We can also search for the type of a value. So we can say type and then give a type name. For example, these type names can be string or decimal or int or long or boolean or what have you, to find documents where a certain key, an attribute with a key, takes a certain value with a certain type. So let's have a look at this example here. We're looking for documents whose runtime is a number. And we see that the runtime here has a number as its value. So we return the document. Yeah. Here we have a different query where we're going to try to search for genres that have an array as a value. Yeah. So here we see genre. Genre has an array as a value. So will we return the document? Yes, we will return the document. Or will we? No, we won't. What happened here? Well, this is the consequence of what we saw earlier, that MongoDB decides to transparently look inside arrays. Yeah, so what it's actually doing here is it's looking inside the array to see if anything in here is of type array. Okay, so this looks very strange. It's a kind of a consequence of this decision to conflate two things we saw earlier. So yeah, what the documentation states essentially is that matching for type array, the document will match it if the field has a nested array. So if it's an array of arrays, yeah. So really here it would return the document if we put type string, because the arrays contain strings. So yeah, my memes are very outdated these days, but anyways, what if I want to check if the value is an array? Any ideas? We can use a function we saw earlier, which is match. So we can just say if the array contains some value that satisfies the condition true, which is just true for everything, then return that document. We match that document. Okay, so we can use match to find documents where genre is an array, using match and this trick of using the true condition, and then we'll return this document. Can anyone see a case that's missing? Yeah, so we're still missing the empty array. So how do we match the empty array? Well, that's fine. We just have to do if the array is empty, we just have to do an OR. So we do an OR where we do the previous thing and then we match exactly on the empty array with equality. Yeah, so this is how we find if genre has an array. It's pretty intuitive, no? So it's a little bit messy, right? Because of this idea of MongoDB that it will transparently look inside arrays for you. So this comes back to bite us. Whether or not this is a big cost or not, I guess one could argue it's not a major issue. I don't know. It's a little bit inelegant if you ask me. Okay. So other operators, we have some other functions, for example, modulo. So we take the remainder of the division. For example, 5 modulo 3 is 2. We have regex to do regular expression matching on strings. We have text search, where we can do free text search, like we saw with Elasticsearch and so forth. uncertain terms over a string. And we can even specify a condition that's a JavaScript function. So a JavaScript function will accept a JSON array, a JSON document, and we'll have to return true or false to say whether or not it should be returned. In the case of the JavaScript code, it's best to avoid using JavaScript code where we can use something else because this can't be optimized. This requires a sequential scan, which means that we have to read every document in the collection, pass it through the JavaScript code, and see if it returns true or false. So some other features for MongoDB that we'll not cover in the class, but just to be aware that it also has support for such features, geographic features. So we can find, for example, restaurants within 5 kilometers of here, or we can find also some intersection. We have some geometric algebra, so we can figure out what things intersect with each other, what things are within each other, and so forth. And we also have some bitwise features for dealing with bit arrays, which is maybe a slightly unusual feature to have, but okay. So we have ways of dealing with bit arrays. Okay, any questions about selection? Well, good. Okay, so the next feature in the relational algebra and the next group of features in MongoDB are the features relating to projection. So what is projection? Projection basically means that we're going to not return every time the full document, but we can specify some elements of the document that we'd like to return. So projection, we choose what output values we want to write from our documents. So we're going to have key 1 and key 0, which will allow us to either output a field with 1 or suppress a field with 0. So we can either say from this document, return X, Y, and Z, that's 1, or we can say return the entire document, but do not return X, Y, and Z, which is 0, which is suppress. So we also have some features for projection from arrays. If we, instead of returning the full array, we want to return some elements of the array. So let's look at those features for projection. So the first feature is to use 1 to output certain fields. So how does this work? If we have our document here, we've run a selection here. This is the first command of find. And if we want to run a projection, we add a second argument, which is the projection. So the first argument is the selection. The second argument is the projection. So the first argument decides which documents we're going to return. So in this case, we're going to return all documents that have a runtime greater than 30. And this has a runtime of 60, so this matches. And then we're going to return from each document the name, runtime, and network. So here we see we have name, we have runtime, and we don't have network, but we'll return whatever we have available. Yeah. So the projection never affects what documents we return. It only affects what we return for each document. So here we get our results. We have our ID always by default as well, even in the case that we don't specify it here. We have the name and we have the runtime. So we're going to return from every document whatever is available from that document for the projection we specified. If we want, we can also output embedded fields by using the same syntax we saw before. So here we have name and we have rating.average where we want to get this value here from the document. So in our output, we'll get the rating average, but the output will still be nested. So we'll still have a nested average within the field. So field is still nested in the output. Okay, so next we want to output embedded fields from an array. So this is a similar example, but this time instead of just being a nested document, we also have an array of nested documents inside here. So if we do reviews.score, what we're going to get back is an array for reviews where we just keep the score in the nested document. So we see that this is the output here. So we get reviews and score 9.1, score 8.3, and so forth. Yeah. So it projects from within the array. Okay, so that's the one. That's the positive case. What about the negative case? What if we want to return all of the document, but we want to get rid of certain fields? So we don't want to return the series, for example. So in this case, we can use the 0 option. So instead of series 1, we put series 0, which says return everything from the document but series. So we get the ID, we get the name, and we get the runtime. So we cannot combine 0 and 1 because you can see that their semantics are very different. It wouldn't really make sense to combine 0 and 1. except for one particular case. Any ideas or guesses what might be the case where we can combine 0 and 1? To be able to remove the ID. Yeah. So we can use ones, and then we can suppress the ID with 0. Yeah. So this is the only case where it makes sense where we would have zeros and ones. Yeah. So the ID is returned by default. If we want to get rid of it, we use ID 0, and then we can use ones for all the other stuff. Okay, so 0 suppresses ID when the other fields are output. Next, we have some projection that is particular to MongoDB, which is about arrays. So there are some cases here that are not intuitive at all. So we'll maybe have a look in more detail at this. So the first type of projection from an array that we have is array dollar or array peso 1, right? So we have here series peso 1. What this basically says is return the first element of series, if assuming it's an array, that satisfied the selection criteria. So in general, the selection and the projection are completely separate things. So we have, this is a slightly weird feature, but it's like an abbreviation. So basically it says return the first element that satisfies this selection criterion here for series. So series says element match greater than 1, okay? So the first element of this array that matches the selection criteria is the element 2. Okay, so we return 2. Okay, that's one feature. If we want to match something, the first element that matches a different criterion to the selection, what we can use is just element match, same syntax as before. So in this case, we're going to return all documents that have a series greater than 1, which is to say that they have 2 or 3 seasons or series or more. And then we're going to return the first series that is less than 3. Yeah. So what do you think we'll return from this array here? Will we return 1? Will we return 2? Or will we return 3? So 3 doesn't match the condition. 1. Yeah. So we return 1. So this seems a bit counterintuitive because 1 is not greater than 1, right? But it's very important to remember that the selection tells us what documents to return. And after that, its job is done. So we have the document and then the projection is applied, right? So the projection then is applied and it doesn't care about what was done in the selection, except for the previous case, this $sign thing. The projection doesn't care about the selection. It sees a document and it takes the first element of the array that will match that that condition, which will be 1 in this case. Yeah. So this is kind of tricky. It's a common mistake or a common error for this type of projection. Yeah, so the projection is independent of the selection. Okay. So apologies. Yeah, sorry. I see what changed. So here we changed less than to greater than. So basically it means that there's going to be no element returned from the array. There's nothing to satisfy this in the array. So what does MongoDB do? It returns basically the document, the ID of the document, but it doesn't return the array, nor does it return the key. It doesn't return the entire field is dropped. So we don't see anything to do with series here. So essentially, if we have a condition here and nothing in the array satisfies it, we drop the entire thing. So it'll drop the field entirely if no element is projected. Okay, so in this case, we have an array of objects where we have different reviews with users and scores. And now we're going to do a search over the reviews, over the documents, and we're going to return any document that has a series greater than 1, so at least 2 series. And then we're going to project the reviews for that. And we're going to project the first review whose score is greater than 8. So what will happen in this case? We'll essentially return from this the entire object associated with the score greater than 8. Yeah. So again, we have this MongoDB magic of looking inside objects and looking inside arrays in order to extract elements to the output. So we can also apply matches on array of documents. So if we wanted to maybe take a subset of the elements of the array in the projection, we can apply slice. Yeah. So in this case, we're applying slice 2. And here we have our array. So any ideas what array will get out as a result of slice 2? So slice 2 will give us 1 and 2. It essentially says, give me the first n elements of the array. Yeah. So we'll get as an output in our projection, the slice 1 and 2 here. Okay. So we have slice n with n negative. So here we have slice -2. Any ideas what we're going to return? 2 and 3, 3 and 2. Yeah. So we're going to return the last 2 elements of the array, 2 and 3 here. Yeah. We'll keep the order, the original order of the array. We also have slice nm. Okay. So we have slice 2, 2, 1 here. So what does it mean? It skips n and returns m. So we're going to skip 2 and return 1. So we'll return, in this case, 3. Yeah. So we skip 2, 1, 2, and then we read 1, which will be 3. Yep. Okay, so now we have negative n and positive m. So we have slice -2, 1. Any guesses? 1? Okay, seems reasonable. Anybody want to go for 2? So the answer is 2. So yeah, we start from here, we go backwards, we jump back 2, but we always read forward. So 1 is also a perfectly valid response, and the reason why it's 2 is because that's the way MongoDB defines it. So we can skip backwards from the end, but then we need to read forwards when we do the limit. So we get 2. Okay, any questions about projection? No? Okay. So next up, we've looked at queries, basic forms of queries. We'll return to some other types of queries in a little bit, but the next features we have relate to updates, how to insert or update elements in documents that are in our collection. So we see here we have some functions for updates. We can set a value, we can unset a value and remove the key and the value, the entire field. Rename, we can rename a field, which is to change the key of a field. We can set a value only if a new document is created with set on insert. So basically there's this update or save function that can either update a document if it already exists or insert it if it doesn't exist. And if it doesn't exist, in that case, we can use set on insert to set a particular value. For example, the date the document was created. We have increment to increment a number by the value. We have multiply to multiply a number, min to replace values less than min by min, max to replace values greater than max by max. We can also have this function current date to set to something to a current date. Okay, so let's have a look at some examples of how update works. So there's the first thing we can specify optionally is, well, I say optionally, we need to specify it, but we could just have the empty query that matches everything, okay? So here we have a selection criteria for the things that we want to update. So we say, okay, update type scripted, and I want to replace scripted with the type fiction. Actually, all of the scripted series, I want to call them fiction now. So this will essentially update the documents in the collection and will tell us how many documents were matched for the selection criteria and how many documents were modified. And here we have this upserted thing, which is 0. Upserted means we tried to update something, but it was actually inserted. So sometimes if we try to update a document with an ID that doesn't exist, we can set so that if it doesn't exist, rather than update it, we insert a new document for that. So it doesn't happen here. Another thing to mention is multi-true. So by default, and I disagree with this design of MongoDB as well, but okay, by default, if you don't have multi-true, it will just update the first document that it matches with the selection criteria. Yeah. So if you really wanted to match all of the things that match the selection criterion here, you need to specify multi-true, and then it will update all of the documents in the collection that match the selection. Okay, so if we run the query later and try to find the Black Mirror series, here we see that type will be updated with fiction instead of scripted because of our update here. So there are various updates as well relating to arrays in documents. So we can add to set, which can add a value to an array if not already present. So it won't duplicate a value if it already exists. We can pop to delete the first or last value. We can push to append items to the array. We can push all to remove values from the array, and we can pull to remove values that match a condition. Yeah, so we have some ways of operating within arrays. And then when we're pushing or adding values, we also have some sub operators that we can call to post-process the results. So we can use this paste cell here to select the first element matching the query condition. We can do an each to add or push multiple values. We can apply slice to keep the first or last slice values. We can sort the array after pushing, after adding some new elements, we can resort it. We can push values to a specific array index. So we can set that on a push command. So we'll have a couple of examples of things we can do. So here, what we're going to do is we're going to pull all of the types. So we have here our array. We're going to pull all of the types that are in drama or sci-fi, where the language is Spanish. Yeah. Sorry. So no, sorry. So type where type is in drama or sci-fi, and then for languages from the languages array, we're going to pull Spanish. So what this basically means is that we're going to modify this document, and if we query it again, we'll see that we've removed these values that we've added here. So we removed drama. We would also remove sci-fi if it were there, and here we've removed Spanish from the languages. So it allows us to get rid of some values from an array. As another example, in this case, we're looking for documents that have a rating greater than 10. We're going to use the same syntax we saw in the projection, which is basically match the first, which will look at the first example of something in the array that matches the selection criteria. And we're going to set it to 10. Yeah. And then we're going to say multi-true to do this for all of the documents. Okay. So here we have 8, 11, 13, and 9. Any ideas what the resulting array will give us? Let me search for some water. So the document will be matched. I don't have water. Yeah, that's okay. So the document will be matched, right? Because it does have a rating greater than 10. Yeah. So we'll have, then this will set the first element of the array that matches the criteria of the selection, which would be 11, right? And then it will set that to 10. Yeah. So what we would expect here is that we would get as a result 8, 10, 13, and 9. And here we see 8, 10, 13, and 9. So it updates the first element that matches the selection criteria. So a more complex example where we're going to push a new value and then we're going to post-process the results. Yeah. So what we're going to do is push into ratings. We're going to push in the values 4 and 9. So we're going to add 4 and 9 to the ratings array. Then we're going to sort in ascending order. And then we're going to slice 4. We're going to take the first 4 results. So what do we think will be the results, the array resulting from this? So we first push 4 and 9. So we add 4 and 9 to the array. That's what this states here with the push. So the ratings, we add 4 and 9 here. We sort 1, which means sort ascending. So we get 4, 8, 9, 9, 11, 13, and then we slice 4. So we would expect to get 4, 8, 9, 9. Yeah. So push, we can have duplicates. Just to mention, sorry, if we already had something and we wanted to avoid adding it to again, we can use the add to set function rather than push. So add to set means that if it already exists, don't add it. So we wouldn't add 9 again if we used add to set rather than push. Yep. Sí.
Estoy hablando porque en el anterior cuando estábamos viendo la lista, La segunda consulta, como que no tomaba en cuenta lo que hiciera el filtro de arriba, entonces solo mostraba el primero. Pero aquí modificó el segundo.
Entonces tú dices que acá
Porque si hubiese sido una lista, hubiese modificado el 8 en vez del 11.
el 8 en vez del 11. Ah, en este caso sí. Entonces, como, yeah, so your question is why here are we caring about the selection criteria when we do the update? Yeah. So you're saying that here, this thing here should be applied, or this update here should be applied independently of the match, and therefore, when it comes to the update, it should just replace 8, the first element. Yeah. So this syntax here, and it's the same in projection. This $ here is a cheat. It's a cheat. It's a messy cheat in MongoDB that allows you to refer to the first element of the array that matched the selection criteria here. So it's the one case where there is a dependency between the second argument, which could be the projection or the update or whatever it is, and the selection criteria. So this is sort of an exceptional case. So yeah, it's a little bit messy, yeah. But that's how MongoDB defines it. I mean, I get the intention, right? You want to replace the values that you just searched for, or you want to project the values that you just searched for. So it has some sort of an intuition, but it's kind of a little bit messy or inelegant. Yeah. So this is the only example, and there's the same counter example as well in projection, where you can use this $ to refer to the first element of the selection, and that creates a dependency between the two. But yeah, it's a good question. Okay. Any other questions or doubts? Maybe in Zoom? No? Okay. So aside from the select and project features, if we think about the relational algebra, we might say, what about things like union, or what about intersect, or what about join, these sorts of features, yeah? So what we can do certain features that one would expect from the likes of SQL, but then the question is, what does it mean to join two JSON documents? It's not as clear as what it means to join two tables, right? But we can do versions of these things in MongoDB using aggregations and pipelines. So aggregation without grouping, essentially what we're going to be doing is we're going to be taking a collection and we're going to be outputting another collection. In this case, however, we have a certain type of aggregation that has no grouping that allows us to collect an array of unique values for that key. Yeah. So this is db.collection, like .series.distinct, and it gives us back an array of unique values for that key. So we can also count the documents in a collection. Yeah. These functions are a little bit distinct from the others. So just to give an example here, this is from the documentation. We have a collection, which is orders, and then we call distinct on customer ID. And we see customer ID here is A123, A123, B212, A123. And we see that customer IDs are duplicated because they have different orders, for example. And we just want to know, what are the customers in this collection? Yeah, or what are the genres in this collection? Or what are the runtimes in this collection? We can call distinct and then give the key for the distinct values we want, and we'll be returned an array with just the distinct values. Okay, so aside from that, we have pipelines, and pipelines, like in the relational algebra, where we have these operators that allow for transforming relations into relations, possibly one relation into another relation with the unary operators, possibly multiple, two relations into one relation via binary operators. We have this notion of pipelines in MongoDB that allows for transforming collections into collections. In this case, these are all unary collections, but we can actually also have binary operators to combine two collections into one. So the stage operators that we can, essentially the operators of our pipeline, we can see as follows. So we can take one collection and apply a match to filter by the selection criteria. So the outputs collection will just have all the documents matching sigma, the selection criteria. We can perform a projection to just extract some of the values from the documents and create a new collection. We can apply a group, which we can group documents by a key or value, for example, to group all of the series with a certain genre. And then we can use aggregate functions like sum, average, first, last, min, max to find some aggregate value over each group. We can apply a left outer join with lookup, where we're allowed to extend the information or enrich the information of one collection with the data from another collection. We can use unwind to compute essentially a Cartesian product for each array value, which we'll talk about. We have call stats, which will give us a collection that just contains statistics about the first collection. It'll just contain one JSON document with a bunch of statistics. We can apply a count, which will just give us a document with the count. We can apply a sort to sort the documents by a given key value, producing another collection. We can limit, sample, skip to return some sample or subset of the documents in the first collection in the output collection. And then we can also save a collection to MongoDB, which is kind of like a final stage operator. So this allows us to take a collection and then transform it and change it and do whatever we want to it. And then we can also optionally at the end output that, or we can save it back to MongoDB for further querying to create essentially what would be a view in the MongoDB sense. And there's more besides. So these are the main ones. So there's a link to the documentation with more information. So we'll take a couple of examples of prominent pipeline operators. Here we have aggregate, which is the function we call on the collection in order to invoke this pipeline of operators. And within this pipeline, and this example is from the MongoDB documentation, the first thing we have is a match, which basically states that we want to return only the documents that have status A. And upon these documents, then we want to apply a group on customer ID, and we want to take the sum of the amount as the value total. So here's our input collection called orders. We first apply the match, and we only keep all of those documents that have status A. And then afterwards, we group by the customer ID. Here we see there's two documents with this ID, and we apply the sum on the amount, which it will be 750, and we store that as total. So here in this case, there's only one element in the group, so the total will be equal to the amount, which is 200. Yeah. So in this way, we can put together a pipeline of operators that will transform one or more collections into a new collection. So in terms of an example of a binary operator, we have this lookup, which is particularly interesting because it's a join, and we know how important joins are in databases in general. So the type of join we're going to apply here is a left outer join. And this has a lot of sense because often in JSON we have incomplete data and so forth. So here we have one collection which describes some series and some country. Here we have another collection which describes channels or networks. So HBO is a US channel and so forth. So what we'd like to do now is to do a join to maybe guess what possible networks these series might be shown on. Yeah. So maybe. So what we'd like to do is do a join somehow country here in the left connection with nation here in the right collection. Yeah. So we'd like to get here information that this could be HBO or Fox, and in this case, well, there doesn't seem to be any network available that we know of. So in order to do this join, we use the lookup operator, and we say from networks, which is basically this collection here. We want to say that the local field will be country. And we want to say that the foreign field will be nation. So we want to join country here with nation here. And we want to store the results as possible networks. So we need to name the new fields that will result from this enriching of data from the join. So, sorry, just to mention that this collection here is named in the call to the function. So this is the left collection here, and this is the right collection here. And then we apply a left join. So why is it a left join? If we look at the results, here we get the resulting data, where here we have maintained the structure of the left collection, but we've added this new field possible networks as was named here. And within this, we've collected an array of all of the compatible documents in the right collection. Yeah. So here the country is US. So here in the possible networks, we'll have an array of all the documents that have nation equals US here. In the case of the Black Mirror UK, where there's no matches, what happens? We still keep the document from the left-hand side. This is why I say it's a left join. We don't remove that document. Yeah. So we keep that document and we add as possible networks just an empty array to say that there is no matches found on the right-hand side. Yeah. So for this reason, it's sort of like a JSON version of a left outer join. The other weird kind of feature that I mentioned that might not be super clear, so worth illustrating, is the unwind feature. Yeah. So the unwind feature, how does it work? We have here our document where we have a name, the wire, and we have our genres. So we have drama, crime, and thriller. Yeah. So what do we do with unwind? Unwind is going to take the Cartesian product of these values in the array. So how many documents would we expect in the output collection? Any ideas? Yeah. So we're going to unwind genre. And what this means is we take the Cartesian product, we just basically flatten the structure, and for every element of the array, we create a new document. Yeah. So now we unnest somehow the array. So this is the unwind operation in MongoDB. The other stuff is relatively straightforward, I would say, relatively familiar from relational databases and something similar. So, okay, any questions on that? All good? Any questions? Okay, so indexing. If we want to query MongoDB efficiently, we need to know a little bit about indexing. So the big advantage of MongoDB versus a key value store is we can do searches and queries over documents, not just given a key, find the value, right? We can also index elements of the document to make that these sorts of queries more efficient. So we have for each collection, we can have an ID on index, which is almost always a good idea. We can have a single field index, which allows us to index the content of, for example, index the genre or index the type or index whatever field we're interested in searching on. We can have a compound index, which will allow us to index multiple fields, to say that we're often interested in querying multiple fields in the document. We have a multi-key index, which is good for indexing arrays, for finding arrays that contain a certain value or contain a certain list of values and so forth. We have geospatial indexes, which are great for find points near to this point, find restaurants close to here, these sorts of queries, which we haven't really spoken about too much in detail. We have a full text index, which is essentially an inverted index, like we saw in the previous classes. So this is for full text search. And we have hash-based indexing if we want to do hash partitioning. If we're not interested in range queries and we want to do a typical hash index from a relational database. These indexes are per collection, so we index at the level of a collection. Yeah. So let's have a look at some text indexing, for example. So here we're going to state that we want to create a new index, and we want to create the new index on the summary key with the type text. Yeah. So this says create a new index on summary of type text. So we're going to create an inverted index here over the text of the summary. Yeah. So if we want to see the indexes that are created within a collection, we can call get indexes. And here we see that there are two indexes available currently for this collection. The first is an index on ID, and the second is an index on the text of summary. Yeah, and it gives some configuration here that the default language is English for normalization. And that the text index version is 3. I guess this is some version of the inverted index, and that the language override is language. So by default, it will index the English language. But if we wanted to index or normalize the text according to a different language like Spanish, that we can add an attribute here. I'm not sure exactly where it goes. Maybe it goes in some nested document, but we can add an attribute in the document to say, rather index this text according to this, a normalization for Spanish, for example, or a different language. Okay, So we've created our index. The nice thing about this is that we can now do efficiently searches on our document similar to Elasticsearch. Elasticsearch is particularly good for this, but MongoDB also has this feature where we can then search within different fields of our documents to find text according to documents according to keyword search. For example, dystopia sci-fi. We would expect a match here. And we get this match. Okay. So as part of this course, you might be waiting to hear about the distribution. So MongoDB, in brief, we've already covered this quite a few times in the course, how to distribute things. So it provides the two main options that we've seen thus far in the course. So what it calls shards, shards is a typical name. The idea of shards is that they're just partitions of the data, distributed to a particular machine. And MongoDB has two options that really depends on the index. So if you apply a hash-based partitioning or a hash-based index, then it will be sharded by hash. However, if you use a sorted index, then it will be horizontal range partition. So this means that there will be chunks of data that are in sorted order will be partitioned to different machines. So hash-based is similar to the Dynamo stuff we saw in the last class. Horizontal range is similar to what Bigtable was applying. So we also have replication. These are called replica sets. So we can have 2 or 3 or 4 or 5 copies, however many copies we want of the collection. So we also have an ability to call map reduce, which we can implement with our typical map and reduce functions, which we can write in JavaScript. So we can write a map function in JavaScript and a reduce function in JavaScript and call on a collection this map reduce function. So the function here is the classic iterate over all of the documents, and for each document emit some key value pair. And then the function here for the reduce accepts a key such as a customer ID and all of the values associated with that key, such as the amounts, and then apply some function over those, in this case to sum the values. So after we've applied this map and reduce, sorry, this is not part of the reduce here. This is the map here on one line. This is the reduce here on one line. We can apply a query to select what we're interested in, and then create our output to name the output of the collection that we're going to write. So here we see our orders. Oh, sorry. The query goes before on top of the collection. On the input collection, we apply the query, then the map, then the reduce, then we name the output with out. So here's our input collection orders, which is this thing here. So we see customer IDs and amounts and status and so forth. So we run the query. This is this query here, which gives us status A. It returns all of the documents here that contain that status A. Then we apply the map, which will, for every document here in this collection, it will emit a pair with the customer ID and amount. These will get grouped together. So here we have the key, customer ID, and the different amounts for that. We apply the reduce function, and then we get this output collection here. So the main thing is we can apply a sort of map reduce function as well, if we'd like to process or transform our collection. Any questions or doubts on that? All good. Okay, so we have features that we can run MongoDB on multiple machines, and we have all the typical things we would expect, such as sharding or partitioning based on horizontal range and hashing. We even have this internal map reduce engine that we can use if we want to aggregate lots of our very large collections. A word of caution about MongoDB before you go off running to use it to build your clinical application with millions of health records of your clients. There are people who have published a lot of criticisms of MongoDB. These are perhaps harsh, but these are newer technologies. They've been around now for a while, well over 10 years, probably 13, 14 years in the case of MongoDB. So they are maturing, but they still don't have quite the maturity and stability of relational databases. So you can find online different criticisms and different news stories about MongoDB having various security problems and not being the most secure ever. So MongoDB is also claims to be open source, but it's not really open source. There's this question about it has a limitation on how it's used in cloud services, which means that it's sort of limited open source in a way. You and I have access to use it, but Amazon can't just offer instances with MongoDB on it. And there's also questions about some of the claims that they've made about their consistency in the case of transactions and so forth. So what's the point there? I think the point is you don't have to be super worried about this, but definitely have a look at this and think twice about using something like MongoDB or any of the NoSQL stores if you're working with sensitive data via a public application. Yeah. So you just need to maybe look. I'm not saying don't use them. I'm just saying do your own research and make sure that it's okay. Yeah. So in general, a lot of these actually, for example, this case here, MongoDB is super popular because it was very easy to install and very easy to start using and running initial queries over. So the trade-off for that is that they basically had configured all these default configurations, which basically had default passwords and everything that you didn't have to configure them at the start. So a lot of it was related to naive configurations of MongoDB databases, not necessarily a problem with the technology itself. But in any case, the point there is just to be a little bit wary about using MongoDB and maybe in general NoSQL systems for very highly sensitive data. So to do your research beforehand. Okay, so why is MongoDB so popular? As we see here, MongoDB is the 5th most popular database engine in this list, after Oracle, MySQL, Microsoft SQL Server, and Postgres, which all of you probably have heard of before this course. So MongoDB is also even gaining on Postgres, right? So why is it so popular? So in general, MongoDB is very popular with web developers because it's very easy to basically work with the data in a database in JSON. So rather than having to have a relational database there where you receive some data and then you need to process it and then maybe formulate it as JSON, JSON is very convenient. It's a very common data format used for web development. And there are like various stacks of technology. So this idea of kind of having these systems or frameworks that work together very well. A very popular framework is called the mean stack. This is MongoDB, Express, Angular, and Node.js. So MongoDB is your data system for your data layer. Then you have your logic, or you have your client side, server side layers, which would be Express and Node.js, Express running in Node.js. And then on the client side, you have AngularJS. So you have some sort of JavaScript, pure JavaScript stack where you can work with JSON data. JSON, I mean, you don't have to use MongoDB in a mean stack. You can use MongoDB in whatever stack you like because you can process very easily JSON data as well. And in pretty much any programming language, you could also have it in something in Python or in some other PHP or whatever you'd like to use. So the idea of being able to store natively JSON data and retrieve natively JSON data proves to be very convenient rather than having to do this round trip through a relational database. So you can get your data for your web page in JSON and use that to populate whatever information you need in your web page. It's not only used in web development, it's also useful in many cases where the schema is not super certain beforehand, and it can be where it's more convenient to store semi-structured data. So that's MongoDB, and that's pretty much all I wanted to present. Any questions or doubts? No? So we'll have the lab on Wednesday on MongoDB. Also, if there's questions in the chat, you can in Zoom, you can drop your questions there. We'll have the lab on Wednesday. The lab will be on, you guessed it, MongoDB. So this will be the second last lab. We'll have another lab then next week. We're going to be looking at graph databases. So we'll have a class of graph databases, and in the last lab, we're going to look at a graph database system called Neo4j, and that will be the last lab. Then we're going to focus on projects from then on out. So Yep, no questions? No? Okay, see you on Wednesday then. Okay. Any questions in Zoom? Okay, if not, see you on Wednesday.